Our final speaker for this afternoon, is Professor Tiffany Summerscales, Professor of Physics. She's a member of the LIGO Gravitational Wave Observatory collaboration. And so she has articles that have hundreds of authors, and I believe the latest one had 3,400 authors. That may set the Guinness Book of World Records of authorship. But she's going to talk to us about the gravitational wave astronomy.
All right. So I want to thank everyone for coming. Today I'm going to be talking to you about LIGO, about gravitational waves, and about the new kind of astronomy that we can do with gravitational waves and the things that we've been able to learn that nobody knew about before. So first off, just a brief description of what gravitational waves are. So they are a fundamental prediction of Einstein's theory of general relativity, which states that gravity is caused by masses curving space and curving space-time. But if there's a change in those masses, then the curvature has to change, and that change propagates outward, much like ripples on a pond. And gravitational waves will stretch and squeeze the space that they pass through, but this isn't something we notice happening in everyday life, and that's because gravitational waves are also incredibly weak. If you used the entire planet Earth as your detector and looked for changes in its diameter, you would find the diameter of Earth changing by less than the width of a proton when gravitational waves pass through. So obviously, we're going to need a very special and very sensitive detector in order to measure these very faint ripples. So the detectors are what is called interferometers because they use the interference of light to detect gravitational waves. And the way that this works is that you have a laser, and the laser shines on a beam-splitting mirror, and then the light goes to two end mirrors and then is reflected back. So if we look at what's happening in detail, the light is a wave. It travels to these end mirrors, which are 4 kilometers away from the beam splitter. Then the light is sent back to the beam splitter where it recombines with the light from the other mirror. Now the light normally interferes. That means the one wave cancels out the other wave and you don't get any light. But when a gravitational wave comes through, it stretches the distance of one arm and compresses the other. And so now you no longer have that mismatch and you get light at the output port. So an interferometer is a way to very sensitively detect changes in the lengths of these arms, which in the case of the LIGO detectors are about 4 kilometers long. So there is a family of detectors all over the Earth looking for these gravitational waves. The ones that I work with are the LIGO detectors that are located in Hanford, Washington and Livingston, Louisiana. And these are these were paid for by the National Science Foundation and are operated by the LIGO collaboration. We also work very closely with Virgo. Virgo is a detector which is located in Italy. And there is a fourth detector called GEO 600, which is located in Germany. Now, the GEO 600 detector is much smaller than the other three. It has arms that are only 600 meters long, as opposed to a few kilometers. But GEO 600 is still very important, even though it can't detect gravitational waves, because we use it as a test bed for new technologies that are later implemented in the larger detectors. In addition to these 4 operational detectors, there are detectors that are in the process of being built. One is located in Japan called the Kagra detector, which is currently under construction underground in what used to be a mine. And there is another detector called LIGO India, or Indigo, which is currently undergoing site selection. And once they've nailed down where they want to build it, then construction is going to begin. So the 3 detectors have been trying very hard to measure gravitational waves, the LIGO and the Virgo detectors. They were constructed in the early 2000s and were run for a few years looking for gravitational waves, and they did not find any during that time. Then they were taken offline and underwent a series of upgrades to improve all of their components, new lasers, better mirrors, better suspensions, and they were then turned back on in 2015. And almost immediately after these advanced detectors were turned back on, nature was very kind to us. And we were able to measure gravitational waves and the LIGO detectors for the very first time. Unfortunately, when this gravitational wave passed through the Earth, the LIGO detectors were online, but the Virgo detectors were still undergoing upgrades, so the Virgo detector didn't measure it. But this gravitational wave was given the name 150914. That refers to the date on which it was measured. So the 14th of September in the year 2015. And in this plot here, you can see the actual data that was measured by the Hanford and the Livingston detectors. So what the gravitational wave that they measured, that gravitational wave was from a pair of black holes that were orbiting around each other. And those two black holes had masses of 29 times the mass of the sun, or 29 solar masses, and 36 times the mass of the sun. And these two black holes were spiraling around each other, and as they spiraled around each other, as they orbited, they emitted gravitational waves. And the gravitational waves carried away some of that orbital energy, and so the black holes orbited closer and closer, faster and faster, until finally they collided with each other, merged into a single larger black hole that had a mass of 62 solar masses. Now, if you're good at doing math in your head, you add together 29 plus 36. Does that equal 62? No, there seems to be a little bit of mass missing. And actually, what happened was that 3 solar masses worth of energy, because Einstein says mass and energy, pretty much two sides of the same coin, 3 solar masses of energy was emitted in the form of gravitational waves. So a whole bunch of energy was released out into space. And you can see why this system was so good at producing gravitational waves. This graph here shows the velocity of the two black holes as they were spinning around each other. And you can see that as the separation went down, the velocity went up. And right before they collided with each other, they were traveling at over half the speed of light. So you can imagine these many tens of solar mass black holes traveling near the speed of light. This was a system that was very good at making gravitational waves. So in these other plots, this one and this one, we can see some smoother curves, and those are the waveforms that were predicted by computer simulations. So we made models of this system using supercomputers and predicted what kinds of gravitational waves should be put out, and that was the prediction, which is very close to what we actually measured. And that tells us that relativity was doing a very good job of telling us what these black holes should be doing and the gravitational waves that they should be producing. In fact, when we subtract the prediction from the actual data, what we're left with is just detector noise. And then this final set of panels shows just a different view of the wave in terms of its frequency versus time. So the wiggles get faster and faster and closer together, so the frequency increases with time. So everyone was really excited when we measured gravitational waves for the first time, because they showed us that Einstein's theory of relativity was correct, and we have a new way of studying these objects. But it turns out that the universe was not done being very kind to us. So just a little time later, on December 26th, so we affectionately call this the Boxing Day event, on December 26th of 2015, yet another gravitational wave signal from the merger of two large black holes was measured. And this time we had a 14 solar mass and an 8 solar mass black hole collide to form a 21 solar mass black hole. And this occurred about 1.3 billion light years away from Earth, which was about the same distance as the first signal. After this pair of black holes colliding was measured, the detectors once again were taken down for a period of time to be made more sensitive, and when they were turned back on, we measured yet another gravitational wave event, this time from a 31 solar mass and 20 solar mass black hole merging to form a 49 solar mass black hole, 2 billion light years away. And then yet again, more recently, it was announced that we had measured a 31 and 25 solar mass black hole, and they combined to form a 53 solar mass black hole. And everyone was really excited about this last event because for the first time, Virgo was able to join the party. So this was the first signal that was seen in all three detectors, and that allowed us to do a much better job of triangulating where on the sky the signal was coming from. So with just the LIGO detectors, we could narrow things down to this sort of arc shape, but with Virgo, we were able to do much better and really pinpoint where on the sky the signal is coming from. And this is super important because ultimately what we want to do is say to our astronomer colleagues with their optical telescopes, look here and see if you can see the event that's making these gravitational waves. And we can't really do that if it's like, look here at this region of sky, huge region of sky, and see if you see anything. We have to narrow things down more for them. So it was great to finally have 3 detectors and really be able to pinpoint where that signal was coming from. So this is a movie that shows a computer animation of what it would look like if you were in a spaceship near these merging black holes. So you would see the light from distant stars being curved around by the black holes, and you would see these black holes orbiting each other, and they are emitting gravitational waves, which you can kind of see by the images of these stars sort of sloshing around. And the black holes, as they orbit, they go faster, and they also get closer together until they merge into a final black hole. Okay, so to summarize the black hole events that we've seen thus far, so we've talked about 4 different black hole events, and in this picture here it shows where on the sky we think the black holes were when they emitted the gravitational waves. And you can see that there are these patches, these arcs in the sky where we think they were located, and we can do such a much better job at pinpointing location with the Virgo detector, with using 3 detectors as opposed to just 2. Another thing you may notice about this chart, we talked about these 4 different black hole events, but you'll see there's this 5th one here, this LVT, that's labeled a little bit differently, and it's over on this chart as well. And what that was a signal that we think is also a black hole coalescence that produced a signal in the detectors, but this one was very much weaker than the other ones. It was much weaker, much more buried in the noise of our data, so we can't be 100% sure that it was a signal. We're fairly certain it was a signal, but we don't have the level of confidence as with the other ones. And so instead of calling it a gravitational wave event, we call it a LIGO-Virgo trigger instead, to distinguish it from the others. So in this chart over here, this is a summary according to mass, how big were these black holes that we saw merging? So the first event is here. We have these 2 black holes. They merge to form a bigger one, as well as these events. And then we also have these purple circles, and the purple circles are from X-ray studies. These were black holes. These were all of the stellar mass black holes that we knew about before we started being able to measure gravitational waves. And we found out these from X-ray studies, which I'll describe a little bit later on. So these were found with light using telescopes that can measure X-rays. But these are all of the stellar mass black holes that we know to date. So where do these stellar mass black holes come from? So all of the black holes that LIGO has measured gravitational waves from so far come from stars at the ends of their lifetimes. So when very, very massive stars die, they can form a black hole. Now, if you have a star that's about the mass of the sun or less than the mass of the sun, when it gets to the end of its lifetime and uses up all of the elements in its core that it can fuse together, then it will first get puffy and it will blow off its outer layers, and then the middle of the star will collapse because it's no longer producing heat and light that keeps it from crunching down. And so when it runs out of fuel, the core will crunch down and become something called a white dwarf. If you have a much bigger star, so a few times the mass of the sun, when that star reaches the end of its life, it has more mass in its core, and so its core will crunch down even harder. In fact, it will crunch down so hard that the electrons will be forced into the nuclei of all of the atoms. The electrons merge with the protons, and you get just a big ball of neutrons, which is something that is totally weird and something we can't even make on Earth in the most sophisticated laboratories. So when that happens, when you get this big crunching down of the core of the star, the outer layers come crashing down. They hit this nuclear material, which is very stiff, and it bounces off and creates this huge supernova explosion. And the outer layers get flung away, and you are left with a neutron star. Now, if you have an even bigger star, when it crunches down and its center collapses, not even neutrons are strong enough to prevent the collapse, and it collapses down into a black hole. And so this is where all of the black holes that we've measured gravitational waves from, this is their origin. But I mentioned to you before that we did know about black holes previously from X-ray studies. And this is a little diagram of the Chandra X-ray Observatory, and here's a picture it took of what we believe is a black hole. Now, some of you may be thinking, wait a minute, I thought the deal with black holes is they don't give off light. You know, they're black, they don't give off light, and that's true. But if the black hole has a companion, if you had two stars orbiting each other, one of them collapses at the end of its life to form a black hole, then it can steal material off its companion star, and that material starts to orbit the black hole and heats up. And that very hot material can then generate X-rays, and that is what we see. We see this very hot material that is orbiting very close to a black hole. There are other black holes out there that we can see that doesn't use this technique. In fact, in the very center of our galaxy, there is a supermassive black hole. Now, these stellar mass black holes that form from stars dying, those can be a few solar masses to a few tens of solar masses. Supermassive black holes have hundreds of thousands to millions of solar masses. And so over here I have a little movie. It's a time-lapse movie. You can watch the year count up. And this time-lapse movie is showing the stars in the very center of our own Milky Way galaxy. And you can see that they all appear to be orbiting something. And if you do very careful calculations on their orbit to get the mass of the object that they're orbiting, it's not giving off any light, and it's hundreds of thousands of solar masses. So this is a supermassive black hole in the centers of the galaxy. So we did know that black holes existed before from X-ray binaries, and then we also knew about the supermassive black holes. Now, LIGO can't actually measure gravitational waves from supermassive black holes because the ones that they produce have a very low frequency, and you need a detector that's not on the surface of Earth. There's too much noise at low frequencies, so you need a space-based detector to measure gravitational waves from supermassive black holes. So what were we able to learn from these gravitational wave observations from black hole pairs? And one of the things that we were able to learn was, what are these stars like that became the black holes? And what were these stars like right before they became black holes? So if you look at this graph here, this is mass on this axis, and you can see the two masses represented by these two bands, the two masses of the two black holes in the very first gravitational wave detection. And they were very large black holes. We'd never seen stellar mass black holes that were this big before, and so it was a bit of a surprise. We didn't know that they could get quite that big. And by looking at how big they were, we can actually rule out some models of what the stars were like at the ends of their lives right before they became black holes. We can rule out these strong wind models, and to say that a star has a strong wind, it means that it's blowing off a lot of material out of its outer layers, because when a star ages and it gets towards the end of its life, it usually swells up and blows away a lot of material. And if you blow away too much material, you don't have a lot left to form a black hole. So if these black holes are very massive, that means that we must have a weak wind at the end of the star's life so that the star can retain enough mass to become one of these very massive black holes. This also tells us something about the star's metallicity, which is a fancy word astronomers use to talk about how much of things other than hydrogen and helium a star has. Because astronomers will refer to hydrogen and helium as those are the biggest components of all stars, and anything else they call a metal. So stars are mostly hydrogen and helium, but they have a small percentage of other things. And because we can make these very large black holes, that tells us that the metallicity must be very small. Because if you have a higher percentage of things other than hydrogen and helium, you have a hotter star, and so the wind will be stronger. So this tells us, we've been able to see from gravitational waves both what the star was like near the end of its life, and then also how much of the star is elements other than hydrogen and helium. Another thing we've been able to learn about the stars that became these black holes is what kind of environment that they lived in. Because these events all involved binary systems, two black holes orbiting each other. So how did these black holes find each other? And how did it come to be that they were orbiting around each other? And for this, there's two kind of basic possibilities. Either the stars or the black holes that they formed lived in a crowded environment, maybe something like a globular cluster, where you have thousands of stars that are close together and all kind of orbiting chaotically around each other. Maybe you had a couple stars or the black holes, after they formed, find each other in that crowded environment and then start orbiting each other. The other possibility is maybe you had a binary system that was a binary system all along. Maybe you had a couple of stars that started out near each other, that lived their entire lives together, then both became black holes and then orbited into each other in the end. Now, how do we distinguish between these two scenarios? Well, we look at the spin of the two black holes, because we expect that in a crowded environment like the globular cluster, if these stars or black holes came together near the end, then their spins would be oriented pretty much randomly, and they would not be oriented together. Whereas if you had a pair of stars that spent their whole lives together, then you would expect they would have a lot of time to influence each other. Their spins would be aligned and aligned with their orbit around each other. And by looking at the gravitational waves, we've been able to see that it seems like this second scenario is more common. So the black holes that we're seeing are from stars that spent their entire lives together. So that was all very exciting. We were able to learn a lot about black holes, how big the black holes were, and what the stars were like that made these black holes. But we always wanted a little bit more, different kinds of systems. We knew there were other things that should produce gravitational waves. And just a few weeks ago, there was a big announcement that that had finally been accomplished. So the big announcement had to do with the discovery of gravitational waves from a pair of neutron stars, which are made when you have stars that are not heavy enough to make black holes, but too heavy to make white dwarfs. So it's that middle scenario. And so what happened when this binary system was discovered is you had, once again, a gravitational wave signal that increased in frequency and in amplitude. But one big difference from the black hole signals is that it was much longer. The black hole signals lasted a few tenths of a second, whereas this signal lasted for quite a few seconds. So these neutron stars that were orbiting each other, they collided, and then 2 seconds later, there was a flash of gamma rays. And gamma rays are the very highest energy form of light, and this flash was seen by two orbiting observatories, the Fermi Observatory and the Integral Observatory. And if you do triangulation, or sort of triangulation, with the arrival times of this gamma ray flash between these two observatories, you can see an estimate of sky location that's a big ring on the sky. Now, in addition, Fermi has a module on it which can determine roughly where the gamma ray flash is coming from, and that's represented by the purple circle. And then this green cigar is where the LIGO and Virgo detectors said the gravitational wave signal was coming from. And as you can see, all three of those things agree, which was very good news, indicating the gamma ray flash and the gravitational wave source were one and the same. Then 11 hours later, this little orange star was put on the map because 11 hours later, Chile was finally in the right location that you could point a telescope at this location in the sky. And the SWOPE telescope was the first to see a speck of light that had not been there before the gravitational wave event was measured. So in these two pictures, they look kind of weird, and that's because they're actually negatives. Astronomers like to look at negatives because it's easier to see a dark spot on a white background than it is to see a bright spot on a dark background. And a few months before this gravitational wave event happened, the Hubble Space Telescope took a picture, and then the SWOPE telescope took a picture 11 hours after the event. And as you can see, there is this point of light that was not there before. So in this dark splotch is the center of a bright galaxy, and it dims as you go outward. And here, associated with the galaxy, is this new bright speck of light. A few hours after that, the Hubble Space Telescope was also able to get in on the act. And you can see here is an image of that same galaxy, and this little red dot is the light from the merger of these two neutron stars. So this is a movie that shows what we think happened in this neutron star collision. So it's kind of an animation of that event. So first we have the two neutron stars that are orbiting each other and making gravitational waves. They orbit faster and faster and come together. And when they crash into each other, there's a giant explosion that blows out all of this neutron-rich material. And this explosion reddens. And then there is a jet of material because there are twisted up magnetic fields that cast off material, and that jet of material starts colliding then with the gas and dust between the stars, which then glows and produces radio waves. So while the optical signal that we saw with the telescopes, that reddened and faded very quickly, the radio astronomers are still looking at that new point of light and trying to learn more about the collision and its aftermath. So what were we able to learn from this event? It was really exciting because we had not only gravitational waves, but we had light, and we had light across the spectrum, radio waves and gamma rays and X-rays and visible light as well. And all of these different channels brought us different information that we were able to combine and come up with a much better picture of what had happened. So one of the things that we were able to learn was that, yes, indeed, colliding neutron stars can produce bursts of gamma radiation. So gamma ray bursts occur somewhere out in space about once or twice a day. And if you make a graph of how many you have versus, or make a histogram of how many you have, you'll see that they kind of come in two different flavors. There are long duration bursts, and it's thought that these are produced by very powerful supernova explosions. But then there are also short duration bursts that last for less than 2 seconds. And for a while it was thought that maybe, just maybe, these were produced by colliding neutron stars. But now that we have the gravitational wave evidence, we know that that is indeed the case, that many of the short duration gamma ray bursts are from neutron star collisions, and that other gamma ray bursts that we have witnessed are probably due to the same cause. Another thing we were able to learn is by looking at the way that the light from this event changed over time, because it was a very rapidly dimming source of light. So the explosion created light that rapidly dimmed and rapidly reddened. And by looking at the exact way in which that happened and matching it to models of the explosion, astronomers were able to determine that this explosion was producing a lot of heavy elements like gold and uranium. There's a very rich, neutron-rich environment in which these materials readily form. A final thing that we learned that was really interesting is that the gravitational waves from this event gave us a new way of measuring the expansion of the universe. So Edwin Hubble famously was the first person to notice that the universe was expanding. And the way he did that was he measured how quickly the galaxies were moving away from us. So if you have something that's expanding, like a balloon, and you imagine painting galaxies on the surface of the balloon, they move away as the balloon blows up. Another analogy that I like to use is imagine a loaf of raisin bread where the raisins are the galaxies. As the bread rises, the bread expands and the galaxies move away from each other. And the further apart two raisins are, the quicker they'll move apart from each other because the more bread there is in between that's expanding. And that's what Hubble found was going on with the universe. As you look at more distant galaxies, they are moving away from us more rapidly. And this, it turns out, is a fairly difficult measurement to do. It's easy to measure the velocity of a galaxy by looking at the light and how the color of the light changes as the galaxy moves away from us. But getting the distance to a galaxy is kind of tricky. And by measuring gravitational waves, we get a very good estimate of the distance to this particular galaxy because Einstein's theory of relativity tells us exactly how strong the gravitational waves were when they were produced. We can measure how strong they are when they reach the Earth, so we know how far away this galaxy is. So we've been able now to construct our own Hubble plot. There's one data point on it, but we can still get a measurement of the expansion rate of the universe, and we find that it does agree with what astronomers have found previously. And hopefully, as we measure more gravitational wave events, we'll be able to have more than one data point on our plot. Okay, so I just want to, before I end, give a shout out to all the students that have worked with me over the years. These are not all of the students, there have been many more. And they've worked with me. We primarily work on some of the algorithms that combine data from multiple detectors and find the properties of the gravitational waves that are in the detectors. And here's just some of the students that we've had. So if you have any questions, I would be very happy to answer them.